Welcome to The Explainer. Today we're diving into a really frustrating, completely invisible battle that chip engineers fight every single day. Look, we all know our devices rely on billions of transistors firing in perfect sync, right? But physically connecting all of them? It's a massive, microscopic logistical nightmare. So let's explore exactly how chip congestion happens daily and what this literal traffic jam inside your microchip actually looks like.
Okay, let's dive into this with a classic mystery. Imagine you're a physical design engineer. You've placed all your logic gates. Everything looks super neat, organized, and perfectly aligned on your screen. The placement tool is giving you the green light, saying you're good to go. But then you run the routing step, the phase where the actual wires are drawn to connect everything up, and suddenly, bam, thousands of connections just completely fail. They can't be completed. So why does a seemingly flawless chip design suddenly fall apart at this stage? Well, the answer to that is exactly what keeps engineers up at night.
The easiest way to wrap our heads around this failure is by thinking about your morning commute. Picture a massive highway. You've got 100 cars that desperately need to get from point A to point B right this second. But your highway only has 50 available lanes. What happens? You get a total gridlock, a massive traffic jam. In the world of VLSI, it is the exact same principle. You've got a huge number of nets, these electrical signals, that absolutely must pass through a specific physical region of the microchip, but there's just a limited number of routing resources or metal tracks actually available in that physical space.
This daily struggle of routing demand versus physical resources actually has a formal technical term. We call it congestion. In physical design, congestion kicks in the split second your required routing resources exceed your available tracks. The routing demand just totally outpaces the physical space. So the router, which is this incredibly complex piece of software, basically starts panicking. It's struggling to draw the wires, and suddenly you're seeing congested regions, crazy long detours, unroutable nets, and just a totally overwhelming number of DRCs, or design rule check violations. So, who are the real villains causing all this daily mess? Well, there isn't just one. We actually deal with three major offenders on a daily basis. First up, high cell density. If you just pack way too many standard cells into one tiny region, you naturally get a massive spike in local routing demand. Makes sense, right? Second is high pin density. Even if the area itself isn't totally stuffed, using highly complex logic cells like AOI or OAI cells means you got a massive number of pins trying to connect in a really tight space. And the third culprit? Bad macro placement. Think of large memory blocks or pre-designed macros as these giant skyscrapers on our microscopic city map. If they're placed poorly, they will absolutely wreak havoc on your routing landscape.
Let's actually visualize that bad macro placement for a second. Think of it as the macro squeeze. Imagine you have two massive macro blocks, and right between them is this super narrow channel. Now, picture hundreds of critical signals being literally forced to travel through that tiny gap to get to the other side of the chip. It's a brutal physical squeeze. Congestion just spikes immediately. On top of that, routing paths from all sorts of different directions often converge right around the corners of these massive macros. These immediate choke points are where your microscopic traffic jams are basically guaranteed to happen if you haven't planned your layout absolutely perfectly.
And this brilliantly illustrates why engineers can't just wave a magic wand and fix congestion by making the chip huge. Physical design is this incredibly delicate, continuous balancing act of four major constraints: area, timing, power, and congestion. Sure, if you lower your cell utilization to give the router tons of empty space, you might completely eliminate congestion. But now you're wasting incredibly valuable silicon area. And a larger area means longer wires, which completely ruins your timing and burns way more power. Every single day, engineers are trading off between these four constraints. It's like a giant puzzle. You push hard on one, and the other three push right back. Now, what happens if an engineer just decides to ignore the congestion? Well, a pretty terrifying domino effect kicks off. Step 1, the router can't go straight, so it takes these massive routing detours around the traffic jam. Step 2, those longer wires have way more resistance and capacitance, which creates a much larger RC delay. Step 3, because the signal takes way too long to actually reach its destination, you get severe timing degradation. The chip just won't run at the clock speed it was designed for. And step 4, if you have to keep ripping up the design to fix these timing and signal integrity nightmares, you blow right past your tape-out schedule. Literally millions of dollars are on the line, and the whole project timeline just completely collapses. Aside from the physical crowding, we've also got logical culprits to worry about. Take a look at high fan-out nets. Imagine a single signal source that needs to drive 50 different destinations all over the chip at the exact same time.
It's like a massive carpool suddenly arriving at an intersection and splitting into 50 different directions all at once. It creates absolute chaos for the routing tool. To fix this, physical design tools have to step in early. They use clever buffering strategies or high fan-out synthesis techniques to distribute that heavy load way before it completely chokes up the routing tracks.
Now, here is a super crucial detail that beginners often forget, and it heavily complicates the entire layout. We actually have to power this tiny city. The metal layers on a microchip aren't just there for signal routing. We need incredibly robust power and ground networks. And guess what? Power straps occupy the exact same routing tracks that your signals desperately want to use. If a region has heavy power grid requirements, you're left with even fewer resources for the signals to travel through. So power planning and signal routing literally cannot be done in isolation. They have to be planned concurrently right from day one.
Now, what's really interesting about this is how the data can completely lie to you if you aren't paying close attention. Let's say you look at your block and it's showing a 75% average utilization. You might lean back in your chair and think, hey, that's totally fine, I've got plenty of white space. But that average number can completely hide a disastrous reality. Because in one small, highly critical corner of your chip, you might actually be hitting a 95% local utilization. And that localized hotspot, that's going to become an unroutable nightmare. This is exactly why great engineers never just blindly trust the average. They relentlessly hunt for localized density and pin concentration.
To actually find those hidden localized hotspots, modern placement tools give us something incredibly useful: the congestion map. Think of it exactly like a weather radar you'd see on the evening news. Green means low congestion, smooth sailing. Yellow means moderate, traffic is definitely slowing down. But red means severe. It's a massive, critical storm. When an engineer sees a red region popping up on their screen, it's a giant warning sign. It tells them to put on their detective hat and figure out exactly why that specific area is overloaded long before the tool even attempts to route the wires.
Let's move on and see how this builds into an engineer's actual daily debugging workflow. It's a highly structured loop. Step 1, you use that weather map we just talked about to find the hotspot. Step 2, you definitely don't just blindly start moving things around. You have to find the root cause. Is it a bad macro? Are there just too many pins? Step 3, you implement a really targeted change to the floor plan, the placement, or the constraints. Then you run your placement again and double-check the congestion map. If it's clear, you finally move to step 4, route the design, and actually analyze your timing. It's this continuous, very investigative loop.
So what are the actual physical remedies you can apply in that third step? Well, it's a lot like rearranging the furniture in a really cramped apartment. First, you can literally just move the macros to open up wider, better routing channels. Second, you can add blockages or halos. This is basically placing invisible tape on the floor that tells the tool, hey, do not put any standard cells here, which reserves that space strictly for routing. Third, you can use cell padding. This introduces some extra spacing around those highly complex cells that just have way too many pins. And finally, you can simply force the tool to reduce local utilization, basically spreading the cells out to give the router the physical breathing room it really needs. But keep in mind, sometimes the fix isn't physical at all. It's logical. When physically spreading things out starts ruining your area and timing constraints, you have to optimize the netlist itself. This means using your software tools to fundamentally restructure the logic. You can do gate resizing or buffer optimization. You can completely restructure the logic to reduce the overall wire demand and cell count in that overloaded area. You can even do pin swapping to make the physical connections just a bit easier to reach. It's all about being smart and altering the fundamental logic to relieve that intense physical pressure on the chip.
We'll wrap up today's explainer with one of the absolute most critical questions asked in physical design interviews. Can you have good timing but bad congestion? The answer is a resounding yes. Your design might initially meet every single timing requirement perfectly, but if it has poor routability, you are doomed. Because the second the router is forced to take detours to bypass that congestion, those parasitic effects change the timing completely. Timing and congestion absolutely must be optimized together. So the biggest takeaway here is this: don't just patch the red areas on your map. Find out exactly why they became red in the first place. That root cause analysis is the true hallmark of a great physical design engineer, and it's how you actually solve the daily traffic jam inside your microchips. But as we push toward 2-nanometer nodes and start packing billions more transistors into the exact same physical space, it really begs the question, will we eventually hit a hard physical limit where absolutely no amount of clever routing can save us? Think about that for a bit. Thanks so much for joining me on this explainer, and we'll see you next time.